So we have done a lot of problems also with respect to it. So in the synchronous machines, there are, unlike that field winding design, what we saw in the previous class was it field winding design of synchronous machine. So now the synchronous machine is the module 5, and yeah, so let's see some problems associated with synchronous machine. So more or less you have to practice a lot many problems here. So this is, yeah, a 250 kVA, 225 rpm, three phase, 60 hertz. No, this is not 60 hertz. This is 60 HP, I think. Yeah, 2400 volts, delta connected, delta connected, salient pole. Alternator has the following data: salient pole, alternator has following data. So the data associated with the alternator is that I'll write down, stator bore. Stator bore is equal to 2.5 meter. The core length is equal to 0.44 meter. Slot per pole per phase is equal to 3. Slot per pole per phase is equal to 3. And conductor per slot is equal to 4. Slot is equal to 4. One more thing is that, yes, conductor per slot is equal to 4. Circuits per phase is equal to 2. I'll explain you this. Leakage factor is equal to 1.2. Winding factor, winding kW, that is winding factor, is equal to 0.95. If it is not given, you will take it as 0.95. Okay. The flux density, then flux density, okay, B average flux density is equal to the is 1.5 Weber, okay, per meter square. Okay, that is the flux density. The winding depth is 30 mm. That is winding depth is equal to 30 mm. Okay, the ratio of full load field mmf to armature mmf. Okay, the ratio of full load field mmf to armature mmf, is equal to 2. Field winding space factor, okay, field winding field winding space factor is equal to 0.84. Okay, and the field winding dissipates, and the field winding dissipates 1800 watt per meter square of inner and outer surface, without the temperature rise exceeding the permissible, without the temperature rise exceeding the permissible limit. Okay, this is like, okay. Leave 30 mm for insulation. Okay, for insulation, leave 30 mm for insulation. Okay. Insulation, comma, flanges and height of pole shoe along the height of pole. Now it is asking you to find number one, the flux per pole. Okay, this is the question what you have to find. Number two, I'll write it in red what has to be find. Number two is length and width of pole. Okay, length and width of pole. Okay, this is number two. And number three is to winding height. Okay, winding height, winding height, and number four would be pole height. So how do you go about this problem? See, the first thing that you have to do is that you have to get the flux per pole. So in order to get the flux per pole, your synchronous speed you can calculate. Okay, so synchronous speed, how do we calculate synchronous speed? Tell me. Ns is equal to 2f by p. Okay, that is one thing. Or your, if rpm is given, rpm is given from there only, that is 225 rpm. So this is rpm, so ns would be 225 divided by 60, so you get this value, 225 divided by 60, so you get the value of ns. Now another thing is that once you are getting the value of ns, okay, yeah, this actually it's 60 hertz only. Okay, the frequency over here is 60 hertz. So once you get the value of ns, okay, here, so what next you will do? Hmm? I'm seeing only three people. Okay, Ratika, Ratika, are you able to hear me?
Yes, sir.
So I had asked for flip class. Okay, so are you prepared? Three people name also I mentioned. Who are those three people? Huh? Hello, Ratika, Ratika.
Yes, sir. I don't remember, sir.
Cannot remember. Nelenaki, what? Like, okay, so three people's name I had written, na? Yeah. So those three people be ready with the topics also I have given you for the flip class. It will happen tomorrow Tuesday in the afternoon. Okay. So tell them, huh? So as far as the name, we can see in the link whatever I have stored, so that from there we can know the topics and also ask them to please, because they have to do it. Okay, it is mandatory. And moreover assignments also I'll be giving, and because I was like focused on completing the module, and some quizzes also will happen, so please be prepared. Okay, so tomorrow today I'll upload some assignments, so you have to like within 7 days, okay, submit assignments. So now like this is the problem. Okay, more or less I'm been solving these problems all over again and again, so I want you people also to do some problems. Okay, an active interest is not being shown by the class. Suppose in March there is really a V2 exam with invigilation. It can happen, an eventuality. At that time you should be prepared, right? Hmm? And do you want me to repeat some of the transformer classes, like which I did not write with my digital pen? Yeah, tell me, Ratika. Ratika,
Yes, sir.
do you want some of the classes of transformer to be repeated, because it was like not visible at that time with this digital system? Tell me,
Yes, sir.
some of them you want, huh?
Yes, sir.
Okay. So with this system, it is okay, na? It is convenient. You are able to follow, na? It is clear, na?
Yes, sir.
Okay.
Yes, sir.
So how do you go about this problem? Tell me. So this ns value you calculate. Okay. After that, what you will do? ns value you have done. Okay, ns value you got. After that, what you know the if you have to calculate the number of poles, hmm, ns is equal to what? 2f by p. ns is equal to 2f by p. That formula you know. P is equal to 2f by ns. So from here you can calculate the value of number of poles. So once you get the number of poles, then total number of slots would be equal to what? Tell me the total number of slots. Hmm. Total number of slots are equal to, see, slots per pole per phase. How many slots per pole? See here. If you notice here, slots per pole per phase is equal to 3. Okay, this is there. But circuits per phase is equal to 2. So what does that mean? Circuits per phase. Okay. So you are not taking, you are taking, so, per phase means you have a three phase system. Okay. Three phase system is represented like this. Okay. There would be R, Y, B, and each is being placed at an angle of 120 degree from each other. 120 degree. So circuits in a single phase, if they are one circuit, suppose I have this circuit, phase and neutral. This is a single phase system. Now, if I want to create two circuits per phase, so I can create two circuits. Let this be neutral part. Okay. So here I have one voltage. Here, from here to here I have one voltage. From here to here I have 230 volts. From here to here I have 115 volts. This I give to the lighting system. Okay. Lighting system, I require only this much of voltage. This 230 I give to the heating system. So you must have noticed that we have different plugs in home for heating system, like for geysers, and we have different normal switches and all we have. So we have two circuits. So similarly here it is two circuit system. So if you have to calculate the total number of slots, it will be slots per pole per phase. So this is slots. So slots per pole per phase 3 into 32. And now for one phase there is half slots. Half slot for one phase. For three phase it would be 3 by half. Okay. So this happens to be, total number of slots happens to be, here you calculate the total number of slots. Now once you have calculated the total number of slots, okay, so total number of conductors is equal to what? Total number of conductors, if you have to calculate, is equal to conductor per slot. That is your SS, okay, into ZSS. So this value, that is conductor per slot, you calculated this value, whatever value you got, okay, into 4. Okay, that would be your conductor per slot. Now turns per phase, okay, Z number of conductors is 6 times turns per phase, so you can calculate the turns per phase. Once you have calculated the turns per phase, then the turns are connected in essentially two parallel paths, and voltage, if you see, it is an Y connected system, so you have to divide for the phase voltage by root 3. Once you have divided for the root 3, then you get the phase voltage. Then you can substitute, okay, 4.445 T5 FKW divided by E, because we have some parallel paths. Okay, so if you, and the value of A you have to substitute over there, and you have to get the value of flux. So once you get the value of flux, okay, then you have, I'll be doing this problem. No, note down this problem. Okay, you note down this problem. Okay, have you noted in a notebook? Then I'll be doing it. So see, this is the synchronous speed. First of all, we'll go for the synchronous speed. If we are going to the problem, okay, so what we see is the synchronous speed 225 rpm. So we'll write the given data. Okay, given data, that is like, what is given, that is your n value is given 225 rpm. Okay, your frequency value is given 60 hertz. Okay, It's given a three-phase circuit is there. Okay, stator bore is given 2.5 meter. Core length is given 0.44 meter. Slot per pole per face is given. Slot per pole per face is given. This is given 3. Then conductor per slot is given. Conductor per slot is given. This is given. Conductor per slot is given 4. Circuits per phase. Okay, that just now I explained you. Per phase is given 2. Leakage factor. Leakage factor is given 1.2, and Kw, the winding factor, is given 0.95. Flux density is given. Flux density 1.5. Okay, Weber per meter square. And your ratio of your then winding depth is given. Winding depth. Okay, this is given 30 mm. And a ratio of full load mmf to armature. See, full load mmf to armature mmf, this is also given, and this is equal to 2. Okay, this is the data that has been given. And field winding space factor, that is your key space factor, okay, of the field winding, that is given as 0.84. And field winding dissipates, and field winding dissipates 1800 watts per meter square of inner and outer surface. Okay, that is okay there. Leave and 30 insulation is required. Okay, now what it is asking is to calculate the flux per pole. Okay, the flux per pole. First thing, the number. Second thing, what it is asking is to calculate the length and width of the pole. Okay, length and width of the pole. Width of pole. And the third thing is winding height. Winding height. Winding height. Height. And fourth is pole height. So how do you go about this is, first of all, the ns value, what you know, you will be, yeah, so the ns value you know would be equal to 225 by 60. So when you calculate this 225 by 60, you get around 3.75 rps. Now formula 2, you know that ns is equal to 2f by p. So the number of poles, if you want, p would be equal to 2f. F value is 60 into ns, 3.75. So this p would be equal to 2 into 60 divided by 3.75. That happens to be number of poles. If you approximate, the value is 32. Okay, now the total number of slots. Now the total number of slots, if you have to calculate total number of slots, that would be equal to, okay, slots per pole per phase, that is 3 into 32 per phase. And every circuit is having 1/2. Okay, 2 circuits per phase, because of that this 1/2 comes. So this is around 336. And now total number of conductors. Okay, total number of conductors, if you have to calculate. Okay, so total number of conductors would be equal to, tell me Ratika, how you write total number of conductors? Z would be equal to total number of slots, okay, into conductors per slot. Number total number of slots, that is 336, into conductors per slot. So conductors per slot is given 4. So this is 336 into 4. This would be around 336 into 4. This would be around 1344. So this is one thing. Now you have to see the turns per phase over here. So the turns per phase. Now we know that turns per phase, that your Z is equal to 6 times turn per phase. So you have to calculate the turns per phase would be equal to Z by 6. So that would be equal to 1344 divided by 6, and that value you will get around. Okay. So this 1344 divided by 6, that value will be around 224. Okay. Now this is a Y connected system. Okay. Y connection is there. So in Y connection, your line voltage is root 3 times your phase voltage. So you have to write your phase voltage is root 3. So the E phase would be equal to, so the voltage what was given, the voltage was given to be 2500 kVA. Okay, this is the rating, and the voltage was 2400 volts. So this volts over here, what is this? Yeah, this would be 242. Wait, yeah, this would be 2400 divided by root 3, and this voltage would be 2400 divided by root 3 would be 1390 volts. So once you get this 1390 volts, okay, so after that, what you have to do is that you have to calculate the number one thing is that you need the flux. Okay, the first thing, flux per pole. Now in order to calculate the flux per pole, we know this equation wherein your E phase, that is your E phase, is equal to 4.44. Okay, 4.44 phi T phase. Okay, F into kW. That equation you substitute, you can get the value of phi would be equal to. Now one more important thing is that it is having, okay, circuits like that, circuits per phase is equal to 2. Okay, so here you have to take a factor of a. T phase is like divided into a because there's not a single circuit, so this a value would be equal to 2. So this is one thing that is essential here in this problem. So you have to take this value of a over here. So flux value would be equal to E phase into this a value. Okay, this is because of circuits per pole, circuits per phase is equal to 2. Okay, suppose they, so sometimes they write 3, so you take this a value as 3, usually it is 2 only. So now 4.44 T phase F kW. Now you know E phase value you just now calculated, the E phase value. So the E phase value just now calculated, that was 1390 into 2 divided by 4.44 into T phase. You just now calculated the value of T phase was 224 into 60, and space factor is 0.95. So you get this value over here. So this value over here would be equal to flux per pole. If you calculate this value, you will get around, yeah, around 49 point, yeah, 49 into 10 power minus 3 Weber. So the first value you got. Okay, so are you following this? Yeah, Nelenakshi, are you following this? Nelenakshi,
Yes, sir.
any doubt you are having anywhere, please let me know, huh? In
Okay,
between,
sir.
if you are having any doubt, or like you are like lost the interest in the subject, something like that, after a long time we are meeting, so such a thin population, only 12 students have joined. Is the same with other classes also? You're doing the same thing, huh? Nelanakshi, Diksha, yeah, tell me, yeah, tell me, Nelanakshi, why is,
Sir, it is
yeah,
same only, sir.
same with other classes also?
Yes, sir.
People are not feeling like giving classes, huh? Now is the time, like now you have to prepare for your this thing, your what do you call, placements and other things. So don't like be let your guard down. Okay, now is the time to really work hard. This is the time. इसको लेके जाओ से. Please, yeah, yeah, hello, yeah.
Yes,
So now is the time to really work hard, huh? So it's not,
yes, sir.
you should not let your guard down. So anyways, concentrate and ask others also to join. So where was I? Yeah. So yeah. Yeah, you are able to see now? Yes?
Yes, sir.
Yeah. So this was about it. So now the first part I calculated. Okay. So this has come for 12 marks. Okay. The flux per pole I have calculated. So if you notice, if you do one or two problems of DC induction or transformer is a little different. But when it comes to the machines, rotating machinery, somewhat they are interconnected. So if you learn two, three problems or like these things, so you are able to do more and more problems. Yes, in induction entering bar current, those concepts are a little bit different compared to, but more or less, if you see the slots, the per pole, per phase, these things are remaining constant. You must be thinking that over and over again he is telling, but this is the subject. Now the flux in the pole body, okay, the flux in the pole body would be equal to 1.2. Okay, the flux in the pole body, okay, you have to calculate the flux in the pole body. So this thing I'll rub over here, okay, because we understood. I want to do this in this particular, okay. So so yeah, this triangle comes somehow, I don't understand. Okay, no problem. Yeah, red. Okay, the flux in pole body, how do you give this flux in the pole body? So basically, this is flux in pole body is given by C1 into the flux. Now, what is the C1? C1 is the leakage factor, okay? How much it will leak and how much it will connect. So, the flux in the pole body would be 1.2 times into 49 in 10 power minus 3. So, the Weber, okay? So, this is Weber. This is Weber. Now, important consideration over here is that once you are calculating this, it happens to be 58.8 into 10 power minus 3 Weber. Okay, very good. Now you have to see the area of the pole body. So, area of the pole body would depend upon the flux in the pole body divided by flux density. Okay, so basically, what is flux density? You know, B is equal to 5 by A. Now, if I want A is equal to 5 by B. So, what I write is that same thing from this only. I write area of the pole body, that is area of pole body, area of pole body. So, area of pole body would be equal to AP. AP would be equal to 5P by BP. 5P by BP. BP value also they have given us the BP value. So, the BP value they have given is 1.5. Okay, average flux density. Here somewhere I had written flux density. Yeah, here. Yeah. So I'll take this 58.8 in 10 power minus 3 divided by 1.5. So I get the area of the pole body. So area of the pole body happens to be 39.2 in 10 power minus 3 Weber sorry, Weber will get cancelled. This is Weber per meter square. So area will be this Weber and Weber gets cancelled. It would be in meter square. Area of the pole body would be equal to 39.2, okay, in 10 power minus 3, okay, meter square. This is it. uh, okay, so from here we learned how these things came. So let's rub this. So we have understood this point, you have noted in your notebook. So let's rub this. Okay, okay. Now we need to know the length of pole body. Okay, so the length of pole body, if you want, so the length of pole body would be equal to, that is given, 0.44 meter, and width of pole body. Okay, so the total area, see, it's a rectangular section, area is equal to length LP into width, okay, or breadth BP, let's say. So it is asking us to calculate length and width of the pole. So length and width of the pole. Okay, so area is equal to length of the pole body, okay, and width of the pole body. So length of the armature core is given. So can we calculate the breadth? Okay, area is also known. So breadth would be equal to AP by LP. So this AP value we calculated just now, 39.2. Okay, 39.2 into 10 power minus 3 divided by 0.44. So this total value, if you notice, this happens to be 0.89 meter. Now the current in each phase, if you want to calculate the current in each phase, so current, the total current, this is 25,000 kVA. Okay, and the voltage is, obviously, uh, so the current, if you have to calculate, would be depending upon that voltage. mm, that is the kVA. See, current, see, kVA is equal to 2500. Okay, this 2500 is equal to V phase into I phase. This is a three phase system, so definitely this would be root 3 V phase into I phase. Now if you want to calculate the current I phase, it will be 2500 divided by root 3 into V phase. That is nothing but 1 3. What did we calculate? That value of V phase you take, that is V phase is equal to V phase by root 3. So this value, and the current value will happen to be around 600 amps. So after substituting the value and current in each conductor, because it's a double phase circuit, so it is current in each conductor would be 600 divided by A, that would be equal to 300. Now let's rub this side. Okay, that was 1390 over there, V phase. Okay, 1390. One three nine zero, that side. Okay, now we have rubbed this side. Okay, now what we can write is the current in each phase, we saw 300 amps. So now since there are two circuits per phase, why is this? Because there are two circuits, since there are two circuits per phase. Okay, this is the reason why it is so. Now armature mmf per pole and field mmf as full load, that you have to calculate, and you have to get the height of the field winding. Okay, so now armature mmf per pole would depend upon, okay, the factors, that is your current, okay, and your other factors that you have calculated, that slots per pole per phase, okay, that is your, okay, T phase, and your winding factor, and the number of poles. So the total armature per phase would be equal to, so that you have known, that would be equal to how much? Tell me. See, one more thing is that armature mmf by field mmf, that is equal to 2. So the ratio, the full load mmf by armature mmf is equal to 2. That means if you are calculating your armature mmf, your full load mmf would be twice of it. So let's go for the calculation of armature mmf. Armature mmf would be equal to, this armature mmf formula is there, that is around 2.7 I phase, okay, T phase, kW divided by number of poles. This formula we have derived also. So we'll substitute there 2.7 into 300 in T phase value 224, kW value is given 0.95, and number of poles are 32. So it happens to be around 5370. Now your MMF at full load is twice of it because of this ratio. Okay, so this is 5370, it's twice of it. So this happens to be 10740. uh, Now mmf per meter height of winding. So this mmf per meter height of winding, this particular thing, if we noticed this particular thing, yeah, here I'm wrapping these things. So if we notice this 107040, so this 10, yeah, here this 10740 would be equal to 10 power 4 into square root of SF DF QF, wherein this 10740 is equal to 10 power 4. The value of SF is given 0.84. Okay, diameter of the bore is also given zero point 0.3. I think in millimeters we have to convert in meter, 0.03. QF value also given 1800. So while we are substituting this happens to be around 67300 amps. Okay, 67300 amps. Okay, now one important consideration over here is the height of the field winding would be depending upon what. See this 6700, okay, 10 power 4 into, see, this is like mmf per meter height of winding. This is what mmf per meter height of winding. So this would mean per meter height, that means height of winding into 67800 is equal to 10740. So height of the field winding happens to be 10740 divided by 67800. This is 0.16 meter. Now if you have to calculate the total height, okay, now if in order to calculate the total height of the system, yeah, yeah, so now if you want to go for the total height, so total height would be equal to height of height of pole height of winding plus height of insulation. So insulation, there he has told 30 mm. So 30 mm is in terms of 0.03 meter. Okay, so total height of winding would be equal to height of pole plus height of insulation. So this height you have calculated is 0.16 and the other height is 0.03. So the total height of the winding would be 0.19 meter. So we just now saw that the flux per pole we calculated. Okay, width of the pole we calculated. Okay, winding height also we calculated, and then pole height. So winding height, how much you got? Um the winding 0.89 meter. Okay, and this is the height of the winding that we calculated. Okay, length of the pole body is given from there itself. If you see in the question only, they have mentioned it is 0.44 meter. Any confusion, any doubt, if you are having, please let me know, please. Hmm? See, again, so this is your question. I'll open this. Yeah, so this is a question that has appeared for 12 marks. Okay, we'll read one more time. A 250 kVA, okay, 225 rpm, 3 phase, 60 hertz, 2400 volt, star connected silent pole alternator has following data. Okay, stator bore 2.5 meter, core length 0.44 meter. Now core length is given, so it's seeing length and width of pole. So from that length only we can, slot per pole per phase is equal to 3. Okay, conductor per slot is equal to 4. circuits per phase is equal to 2. So here you have to remember very important thing, like when we are taking E phase at that time 4.44, okay, F T phase kW divided by A, because this is a circuit, per phase is equal to 2. Then leakage factor is 1.2. So flux of the pole body would be equal to leakage factor, that is leakage factor into the flux, main flux. So if this is kept as C1 into 5, C1 is the leakage factor. Okay, binding factor is 0.95 in examination. If it is not given, by default you take 0.95. Average flux density, it is mentioned over here, 1.5 Weber per meter square. Now your winding depth is equal to 30 mm. Okay, so that depth is given there. The ratio of full load mmf to armature mmf, so here you have to remember that formula, that we calculate 2.7 I phase T phase kW, okay, into number of poles. This formula you have to remember. Then one more formula we have calculated. So these formulas, like you, I will make a list of these formulas. So like in induction motor, in transformer, what are the formulas? So although after looking at the derivation, you have to like learn the derivation. If derivation is asked in the examination, so you're easily able to derive. But at times a problem is directly asked, so no need to go for the derivation. Even you, if you remember those formulas, that is also good, because you can directly apply and save time. So those particular 10-15 formulas in every section would be there. So like entering current, bar current, then these formulas now you can keep at your fingertips, and it would be handy in solving the problems. Field winding space factor, again it's given 0.84, and field winding dissipates 1800. Now you must be wondering from where I got this 1800. This was the 1800 watts per meter square of inner and outer surface without the temperature rise exceeding the permissible limit. Oh, and you have to leave 30 mm for insulation. Okay, so at the end I am 0.16 plus 0.003 is from here. Okay, that's what I am adding for insulation. Okay, of height of pole shoe along the height of pole. So the first thing is to find the flux per pole. Second thing is length and width of the pole. In order to get the length is given there. Width, we calculate area. Area, it's a rectangle cross section, length into width. So from here you get the width. Okay, winding height. Okay, the winding height and the pole height. See, the winding height you are calculating. Okay, height of field winding is the winding height. Now the pole height, if you have to calculate, so you have to leave this 30 mm for insulation. The total pole height would be equal to winding height plus the insulation height. Hope you have understood this problem. Any doubts anywhere, you can ask me, please. Yeah, Bhavna, tell me anywhere you are finding any difficulty. Bhavna?
No, sir.
No, no. Some difficulty would be somewhere. Na? If I'm also Dhanush, what about you? Dhanush, 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 are you singing some song? Dhanush, where are you? Dhanush, Bhumika, Bhumika, Manohar. I think each one of you are sleeping now. Nivedita, yeah, Manohar, tell me.
Hello.
Any difficulty anywhere? Please tell me.
No,
Manohar,
sir. I'm fine. Yes, sir.
so have you concentrated in the class? Then only you will find difficulty. If you are not concentrated, then everything sab badhiya hai. If you will concentrate only, then only is possible. Can I ask you something? Yeah. Okay, then today's one homework problem I'll give you. I want you to do this homework problem, and I'll put assignment problems also. Okay. So that in within 7 days you have to give it to me. Okay. So there's one homework problem I'm giving right now. So you do this. Let me check. Yeah. This is a homework problem. So take down this. I'll be asking you in the next session. This is homework. 50 hertz. Yeah, this is for, yeah. This is the homework problem that is appearing on your screen. So tomorrow, like three people have to give the flip class. Okay. So the name of them I'll see in this. Okay. Who? Yeah, Manohar. Yeah, whom I have assigned flip class? Do you remember anything? Huh?
No, sir. No, sir. 2 weeks before, right? I don't remember.
So those people might be remembering now. I can see in my video, no problem, because everything is recorded. So I'm also not remembering now, but I request all of them three to present the flip class tomorrow. Be prepared because some of them told the time is not there. So tomorrow's class would be for flip class. Okay. So all of them three are requested. I'll put in the group message also after checking from the video. So please, okay, those of you who are present, so remember. Anyways, so I'll be winding my class. Only 21 are present. So raise your hands. Yeah. So I can see Danish, Bhumika, Monica. Monica V is not there. Huh? Hmm. Chaitra, Nil, Nakshi, Manohar, Dikshita, and Ajay Kumar, Bhumika, Ratika, Likhit, Avulia, Jason, Prakash Tiwari. Okay. Thank you.